Okay, Marco. Yeah, so about halfway done, so I have those grades for you guys tonight into tomorrow. You won't be able to see your papers until tomorrow, but you should have the grades by tonight. I grade question by question, not necessarily student by student. There was one student that I finished grading because his paper was easy, and he got 118. So apparently I made that test way too easy. So the third test, I'm gonna out of 100. It's out of 100. The test was out of 100. And there were 20 points bonus problems. So yeah, that's crazy.
I hope they all stay there.
Yeah.
So we're going to continue with related rates. Do some more examples. The process is always the same, but the examples can kind of change how you approach it, sort of. So I just want you guys to get used to approaching things from different angles. So remember, the idea is if we know two quantities are related, it turns out their rates are related as well. And so sometimes if you know about the rates of one thing, we can figure out the rates of other things, right? Like, we're talking about the concrete thing. So if we know how the humidity is changing, we can tell how long it's gonna, whether the concrete will take longer or shorter to harden. You know, so like things like that would matter. So if you're making a concrete structure in the summer, like your schedule will be completely different from if you're doing it in some other season, you know, because you have all these things to worry about, right? So, so things are related sometimes, and sometimes their rates are also related whenever that happens, and we want to figure out how they're related. And so there's a process that we always go through when you have a related rates problem. This is talking about rates of change of rates of change of related quantities. Some other key concepts to keep in mind is derivatives are always with respect to time when you're doing related rates. So be careful to make sure you're doing implicit differentiation with respect to t, even if your variables aren't t. Time. And how you would know that it's a related rates, you will be given information. About quantities. And in particular, you'll figure out the rates of some of them. And you'll be asked to find the rates of others. Right, so if someone says, something is moving this fast, find out how fast this other thing is moving that's related to it. Once you know that's the problem, it's a related rates problem. So that's how you'll recognize when you should be doing this. And you'll always go through the same 6 steps, right? So first you read the problem, make sure you understand how things are related, because that's going to help you with that setup. The next step is to draw a diagram if possible or necessary. Usually if you're already given an equation, the relationship between the quantities, you're already given an equation, you don't really need a diagram, right? The diagram is really there to help you figure out how to come up with that equation in the first place, right? So if you're drawing a diagram and you realize, oh, it's a triangle, you can figure out equations that you'll want to use. You might want to use Pythagoras' theorem or something else, right? Or if it's a rectangle, you know, you might want to use length times width if area is important, things like that. So your diagram really helps you figure out the relationship itself. So you read the question, make sure you know how things are related, draw a picture if it's going to help you out. That picture should help you come up with an equation, right? You're going to want to know what you have, right? So you're going to be given some information, right? You're going to be given something and you want to find something else. Make sure you write that down at the beginning, right? Because sometimes things can look convoluted and you'll forget what you're doing. You'll forget what you're supposed to find and all that stuff. So I recommend you write that down before you start anything. Once you have that relationship, you will differentiate with respect to time. You're going to solve for the rate that you want to solve for, plug in all the unknowns. If you end up in a situation where you don't have all the unknowns, you go back to the original equation that you've made and solve for the guys that you don't have. Right? And then you answer the question. That's basically it. right? So it's the same 6 steps you go through all the time. So now we're going to continue. So we did examples 1, 2, 3. So we're going to turn the page. We also did 4. So let's go into 5. So again, remember I gave you a handout. If you lose it, it's posted on my website, so you can just go there and download it and print it again. So we're going to move on to example 5. Okay. So it says a baseball diamond is a square with side 90 feet. A batter hits a ball and runs towards first base at a speed of 24 feet per second, which is faster than Usain Bolt, or whatever. At the rate, and it says, at what rate is his distance changing at what rate is his distance from second base decreasing when he's halfway to first base? So here you see they gave you some information. They told you how fast one guy is moving, and they asked you about the rate of change of something else. So this is a classic related rates problem. So read the question, understand it. It's a one sentence problem. But then we're going to want, so 1, read. 2, diagram. They told us it's a square, so it's a baseball diamond. Hopefully you know a little bit about baseball. This would be, you can call home. This would be first base, second base, third base. Right. So the batter stays at home and he hits the ball and he starts running towards first base. Right? So that's what's going on. Right? And what we want to measure is his rate of change of distance from second base. Right? So let's pretend this guy is right here. Right? That's our runner. Right? This is the batter. Right? And we are measuring his distance from second base. Right? Do you see what's going on? Okay. So this, it's supposed to be a square. Each side here is 90 feet. That's not changing. Right? But what is changing? Remember, when we label our diagram, we want to be very intuitive. We want to label things that are changing with variables, label things that don't change with constants. So the side length of the diamond isn't changing. Right?
Side A is changing.
What's that?
First base line.
This line?
Yeah.
That's not changing.
He's moving. He's not triangle.
Huh?
That second base is bad.
Right. The distance this point is from the edge is changing, right? So because this guy's moving towards that distance is getting smaller. So it's not this first line changing specifically, it's the distance between one of the ends and that guy is changing. So let's say I label this one X. That's always 90, so I can label this one Y, right?
Oh wait, in the first it says he's halfway to first base, so we'll take that into account?
That comes later. Yeah. Right? Right now you want to set up the diagram to encompass the general situation where things are still in motion. Right? So when he's halfway towards first base, that's just talking about an instant. Right? You don't try to draw the instant. You try to draw a diagram that encapsulates the motion. Right? What's moving, what's staying constant. Right? So we are in part A. So that's our diagram for part A. Okay, now that is going to help us come up with a 3. What we're going to want to do now is write down what we know so far and what we want to find. What info do we know so far?
One of the sides of the triangle, 90.
What
The
else?
fact that it's a right triangle.
Sure.
He's running at 24 feet per second.
D,
Right, in terms of rates and that stuff, what rate do we know?
DXDT.
dx dt, right? How fast this gap, this distance here is closing. So dx dt, we know, what is it?
It's 45.
It's 24.
What's the speed?
It says he runs towards first base at a speed of 24 feet per second. Nope. What's happening to x? Is it getting bigger or smaller?
Smaller.
Okay, so what's dx dt?
Negative.
It has to be negative. So dx dt is minus 24. Whenever something is getting smaller or decreasing, the rate is negative, right? Because the slope is going down, right? So that we know, right? So we know how fast x is changing. What do we want?
dy dt.
dy dt, and we want that at a certain instant, right? We want dy dt when what happens? So at what rate is the distance from second base decreasing when he's halfway to first base, right? So halfway to first base means, how do I describe that situation?
When x is 45.
When x is 45, right? Okay, so that's our diagram. We know what we want to find. Now the next thing is we need to find an equation that's going to help us get there, right? So before we come up with that relationship, what's the relationship here?
90 squared plus x squared equals y squared.
Correct, Pythagoras' theorem. Pythagoras, if I take 90 squared plus x squared plus y squared. Step 5 is to differentiate with respect to t. So what do we get?
Well, that 90 squared goes away.
Yeah, it's a constant.
2x dx dt.
Right? We're differentiating with respect to t, so every time you do any variable that's not t, you have to add a prime. Attach a prime to it.
Equals 2y dy dt.
So that's our relationship. I can divide both sides by 2. And so now, what do we want? I want to know dy dt.
Divide by.
So in other words, dy dt. In this case, it's not hard to just solve for it. This is dx dt over y. So now I want to plug guys into here. Now I know what x is. X is 45. Dx dt I know is minus 24. What is y? Right. We don't know what that is, so we always go back to our equation that we set up in step 4 to figure that guy out.
Don't you have a 1, 2, 3 triangle?
Yeah, so there are things like the 3, 4, 5 triangle or the 7, 12, 13 triangle. Those are the most common ones that we use because those numbers don't get too big, and since you don't have a calculator, if it's a special triangle, it'll be one of those guys. So this 90 looks like it's 3 times something, right? So we have this triangle. Let's call that x, y, 90. So it's 3 times
30.
30. But x it's 45. What is that? What? Yeah. This would be 3 times 15. Can I write this as a multiple of 15?
Yes, actually, you can. That's 6 times 15.
Alright, that's 6 times 15.
3, 6, and 4.
So what do we get? Can we represent this as a 3, 4, 5 triangle? No, right? Because that side is double this one. The relationship between 3 and 4 isn't double. So it's not a nice triangle, so we have to do this the old-fashioned way. So I have 90 squared plus 45 squared should give us y squared. This means that our y is equal to the radical, plus or minus technically, but it's a distance, so we're only taking the positive one. Radical of 90 squared plus 45 squared. Now, we know that 90 we could write as 6 times 15. $45 is 3 times 15. There it is. So here, our y is equal to, this is 6 squared times 15 squared plus 3 squared times 15 squared. Notice that 15 squared is a common term. I can factor that out. If I put it outside the radical, it just becomes a 15. So we do 36 plus 9. So it's 15 radical, 45, which I can factor out a 9 from that, right? Because your 45 is 9 times 5. So I can factor that out, I get a 3 when I pull that out. 3 times 15 is?
There's 45.
It's 45 root 5.
Uh,
So now this means that my dy dt is equal to x is 45, dx dt was minus 24 over the y, which is 45 radical 5. My 45's cancel, and I just get minus 24 over radical 5. So that's, and I know that that's decreasing because there's a negative sign, right? So the problem said, find out how fast it's decreasing, right? So because it's a decreasing, I know it's a negative sign. If you didn't get a negative sign, something would be off, right? That would mean increasing. Okay. Now there's a part B. At what rate is the distance from third base increasing at the same moment, right? So here I'd set it up all over again. So this is my baseball diamond. Here's this guy here running. Now I want to measure his distance from that, right? That's third base. Right? So I'm going to call that the y. This time I'll call this the x. That's my 90 degrees, that's my 90. And so now I know my dx dt is actually positive 24 because it's increasing as he runs that way. And I want
dy dt.
dy dt when x is 45. And the computations are going to be very similar because I repositioned my x to get a very similar kind of triangle. So by Pythagoras, the same relationship is going to hold. So let's go through it again. Right, so that's my new diagram by Pythagoras theorem. This is going to hold again. So then after that, I'm going to differentiate with respect to t. Cancel the 2's. My dy dt is equal to x dx dt over y. And so now here my x is 45. My dx dt now is positive 24 because my x is now the distance that's increasing. And this, you would have solved it the same way. So that's 45 radical 5. So it's just the positive of the other one. So it's going to be positive 24 over radical 5. It's because the things are square. Things are kind of, you have symmetry here. That's why it worked out that way. Right? Because that's kind of, those will be pretty much the same thing. Right, so if this was, and it was more elongated, if it wasn't square, it was a rectangle, the numbers might be different. So be careful when you're trying to use symmetry to judge things. Questions on that?
Professor,
Yes.
is it always, are related rates always going to involve like right triangles?
No. Remember our first one was a cylinder. Right? And the second example was actually a cubic function. A particle was moving along a cubic function. Triangles are pretty common though. Let's move on to example 6. And here we're sort of putting an economic spin on things, kind of talking about money again. So we go back to our llama story. Remember the llamas that were in my backyard? So yeah, they're really getting out of hand. I decided to sell them, right? So. Because they're growing really fast. All right, so, okay, so they're breeding to da-da-da. I'm selling X thousand llamas per week, because it's a lot, right, at price P, right? And I figured out this following equation. So right here, notice that I give you the relationship. I tell you that P plus 2X plus XP is equal to 38, right?
And P is the price, right?
P is the price I'm selling the llamas for, X is the number of llamas I'm selling per week in thousands. So now, here, because you're given the relationship, basically what you're going to do is you're going to skip steps 1 and 2, right? You don't need them, right? The whole point of doing steps 1 and 2 is to get to this relationship, right? So I just flat out gave it to you. So right now you can skip those, right? But you're still going through the same order, going through your checklist. So you don't actually need steps 1 and 2. So now we're down to step 3. What do we know? What do we want to find? So
DXDP or DPDX?
So now step 3. Okay. So let's read. Kind of skip step 1. Right. So I want to sell X thousand llamas per week at price P, right? And I realize that this is the relationship that they share somehow. How fast are Jhevon's weekly llama sales changing at the point where he's selling 4,000 llamas per week at the price of $6 per llama? And he's decreasing his price at a rate of 40 cents per week because they weren't selling very well, so I decreased the price.
When you saw that many.
Yeah. Market becomes saturated, and everyone's like, everyone has a llama. Like, I don't want a llama. Everyone has a llama. You know, you can't keep up with the Joneses if both of you have llamas. So I'm kind of okay. So here's what do we know so far. I know that I'm decreasing the price, right? So what does that mean?
So
dx dt equals negative some 0.4.
I'm
DP
decreasing the
dx?
price. What's the price? P is the price. So dp dt is what I know. The rate of change of the price, right? What's that?
negative 0.4.
Negative 0.4. I'm decreasing, so it's negative by 40 cents per week. Okay. What do I want? It says, how fast are the weekly llama sales changing when I'm selling 4,000 llamas? This means I want dx dt, right? That's how fast, how many llamas I'm selling per week, right? When x equals 4, right? So it's in thousands, so it's just 4. And I told you the price I'm selling them at, $6 per llama. So P equals 6 and X equals 4. So now I know what I want and what I want to find. Now I know what I know and what I want to find, and I know the relationship that's going to help me get there. So what's the next step?
Implicitly differentiate. So the first one's going to be just literally dp dt.
Yep.
dp plus 2 2x dx dt.
Derivative of 2x
2
is just 2.
Yeah.
dx dt. What's derivative of x times p?
Wow.
dx dt times p plus x dp dt.
Product rule equals 0. Right? So I differentiate the x, which the derivative is dx dt. Leave the p alone, then I leave the x alone and differentiate the p, which is dp dt. Right? So at this point, I kind of know everything. I know what x is, I know what p is, and I know what dp is. Let me just plug those in. My dp dt is minus 0.4 plus 2 times dx dt is what I don't know. That's what I want to find. Plus dx dt times p, which is 6, plus x, which is 4, times dp dt, which is minus 0.4. And that's all equal to 0. So on this side, I have 8 dx dt's. I'm going to bring these over, so that's 4 times 0.4 becomes positive because that was negative. Bring this over, plus 0.4. So in other words, I have 5 0.4s my dx dt is going to equal to 5 times 0.4 over 8. 5 times 0.4 is what?
2.
It's just 2. Right? 5 times 4 is 20, and the decimal place, so that just becomes 2. So 2 over 8, which is
1/4 or 0.25.
yeah, a quarter. So on average, my weekly llama sales are decreasing by 1/4 of a llama per week. So I sell 1 less llama a month. Yeah, it's not bad. It's a pretty. I should like close down the hot dog stand and just do the llama business. Move on to example 7. All right, read this and you guys try to tell me how to set this up. Superman is cruising at 390 feet per second at an altitude of 500 feet, flies directly over Jhevon's house. I don't know if he's trying to steal one of my llamas. Assuming Superman maintains an altitude and speed, how fast is the distance from Jhevon's house to Superman changing at the time when Superman is 13,000 feet away from Jhevon's house? Okay, what's the picture? So we read it.
Yeah, house and there's a Superman.
There's a house and there's a Superman. Yes.
So they need to find
I assume that the house is somewhere on the ground.
And there's no kryptonite.
No, because he wouldn't be able to maintain his altitude and speed if there was
Would it be a triangle?
Fall.
So what's Superman doing? He's flying over the house, right? That's Superman flying, right? Superman right there. Now his altitude is what? 5,000. Right. So his distance above this distance here is 5,000.
Just a little hair under a mile up.
And so what else is in this diagram?
I mean, which one is it at 13,000? So it would be like.
Yeah, so he's flying past, so at some point he's here, where his distance from the house, right? That distance here is going to be 13,000, right? So I have that here. Okay, how do I label this? What's changing, what's not?
So,
It just
so the
height,
height.
like the length of that triangle, like on top.
What happened?
Like, yeah, so when you, like.
So basically I do have another triangle, it's this guy, right? That's obviously a right triangle.
So now the hypotenuse is not the one with the house, like the one on top, that's changing, right? 'Cause it's
This here is
yeah.
changing, right? Because he's moving, so this is getting longer and longer and longer. So I can call that something like X. What else is changing? The hypotenuse. Well, that's Y. What about this leg?
That's
It's still 5,000. It says he maintains altitude, right? So that's always going to be 5,000. So that's my picture. Okay, so what do I know? What do I want to find?
You want to find,
What do I know?
well, you know for 5,000, you know that,
Usually when we talk about what we know, we're usually talking about in terms of rates.
dx dt.
I know dx dt. I know how fast Superman is flying. How fast is that?
Should really label it ds.
390 feet.
ds dt. DS. Draw the Superman symbol. 390. Right? And I know it's positive because this is increasing as he's moving. Right? So that's something you have to always consider here. Whether the thing you're looking at is decreasing or increasing, that matters. You have to do a sign change to talk about that. So I know that. What do I want? dy dt. At what point?
1300.
What is 13,000?
1300, right?
when Y is,
What X?
Why?
Just 13,000?
Yes, 13,000. So, yeah. So for we're going to set up the relationship, which is square triangle again. So it's Pythagoras' theorem. So I know that y squared is equal to x squared plus 5,000 squared. This means, no surprises here, 2y dy dt equals 2x dx dt. Cancel the 2's, and I want dy dt.
Well, the only thing you really don't know is x. You do know dx, dt, and y.
Right, so what is x?
Well, you plug y into the Pythagoras theorem.
Right.
In order it says solve for x, and yeah.
My y was 13,000.
Mhm.
2x squared plus 5,000.
Subtract 5,000 squared from both sides.
Isn't that a special triangle?
Yeah,
So it's a 5, 12, 13 triangle. So notice this is a 5, 12, 13 triangle. So there's another relationship between, besides 3, 4, 5. There's a 5, 12, 13. Right? Because 169 is equal to 25 plus 144.
Professor,
Yes.
once you, let's say, move 5,000 squared to the other side, if you needed to, and despite the fact that both of those numbers are squared, can I factor out a 1,000 to make
You can
the
factor
number?
out a 1,000 and then work with a 5 and 13. Yeah.
Yeah, okay.
So if you forgot this, you could get there eventually. You'll take a couple more minutes to come up with the numbers. But if you see this, it's just quicker. So we know that if we did solve for all this, our x would end up being 12,000.
Now, it would be, so dy dt is equal to 12,000 times 390 over 13,000. Or 12 over 390 over 13.
So you cancel the 1,000 each. 13 goes into 39, right? 3 times?
Yeah.
So that's 30. So that's just 12 times 30, which is what, 360?
Wait. Oh, yeah, 30.
360. So that's our rate, that's our answer.
So you just like slow down essentially.
What?
You just slow down like a little bit.
Who?
You slow down super good, like you start at 390 and then you go
No, this is the distance between Superman and the house. No, Superman. Superman is maintaining speed. It wouldn't be a slowdown anyway because you'd get negatives if things are slowing down. Well, no, the acceleration. Yeah, but that's not Superman's thing. So there's some more examples here for you guys to try. A couple are from the old finals. So I'll leave that to you guys. If you want to try them at home, you can ask me questions on that tomorrow. That's done with later grades. So the basic idea is there are all these 6 steps. You're always going through the same 6 steps. The difference is the shape might be different and hence the equation might be different. But as long as you get the correct shape, you label it correctly, it should be more of a follow your nose kind of thing at some point. So if there are any questions? Not, we'll move on.
So for those part, the hardest part is usually just the shape and the
Yeah, like once you get up to step 3, the rest is right. It's really the first 2. You have to draw the correct shape and use that to come up with the correct equation. And if you label things, if you don't label things properly, it can cause a lot of confusion. So if you label something that's a constant with a variable, then you have this extra variable around and you're differentiating and you're like, what's going on? So that actually does it with 4.1. Move on to 4.2. We're going to talk about max and min values. Yeah, I think that's all we've. I think after we complete this, we'll stop for today. Graphs comes next. So this is some of the preliminary discussions that will go into finding graphs. Learn about how to find maximum and minimum values of functions. Start with some definitions. Because there are two classes of maximums and minimums that we're going to care about. So here's the first one. It's called an absolute maximum and minimum. So suppose x is a function with domain D, right? So D is the set that represents its domain. And let C be inside of D. Then we have the following definitions. F of C is called an absolute maximum if f of C is greater than or equal to f of x for all x in the domain. Right? This is I don't know if you guys are familiar with this. This is a set theory notation. It just means it's a member of or it's contained in or it's an element of. So this is just saying C is in D, right? So C is just a number in the domain, right? Right, so let C be some x value in my domain, then if I evaluate that at that, if I find the y value, and that y value is larger than all the other y values in that domain, then this number is called the absolute max. This guy is called an absolute min, if the opposite is true. If this guy is less than or equal to every other y value. So let's do some illustrations here. So you get an idea of what I'm talking about. Very similar to a tangent. You're not supposed to know trigger in this class. Did we finish writing this? So remember the definition of absolute max and min? The y value has to be larger than every other y value. Picture. Okay, so just from the pictures, don't worry about what functions these actually represent, what their definitions are algebraically. Can you tell me about the absolute max or absolute min of this one?
Yeah.
Right, so the vertex here, that would be
Why is that?
This is an absolute max, right? Because the y value at this point is larger than every other y value on this function, right? So let's say this is a and that's b and this is c, then f of c is the absolute max. What would the absolute min be? Is there an absolute min?
No.
There's just two values that share the same.
Yeah, but it can be less than or equal to, remember?
Oh, that's right.
So this guy here is an absolute min, right? So f of a is an absolute min. The same token, this is the same value, but f of b is also an absolute min, right? Of course, if you have several absolute mins, they have to actually be the same, right? So, because it has to be less than or equal to everyone else, right? So both of these guys, they're actually equal to 0. They're both absolute mins. That's the highest guy. That's the absolute max. What about here? So say this is A, and that is B.
So A would be the absolute, f of A would be the absolute minimum.
Right, so
And
here.
f of B would be the absolute max.
Yep. That's not bad. What about this guy?
No absolute max, but there's an absolute min.
Right. No absolute max. And if I call this A, then f of A is absolute min. That guy. Do you see why there's no absolute max?
Yeah, is it like the nature of like infinity is continuous?
Right, it keeps going up, right? So any y value I pick, eventually my function is going to pass that. So there is no single y value that's bigger than every other y value. It keeps going up, right? So there's no absolute max. What about this one?
Same thing. There's
Right, this keeps going up, so there's definitely no absolute max. But it also keeps going down, so there's definitely no absolute min. So there's none here. No absolute max or min. What about this function?
Well, the part where it dips down to the lowest, that's the absolute minimum.
Right, so this point here is absolute min, right? Whatever its y value is. So if that's at A, that's this f of A is absolute min. Absolute max?
I guess that ending point right there.
Yeah, this point here. F of B is the absolute max. That's it. So you look at the highest value in general and the lowest value in general. This is called the absolute max and min. Now, there's another name for it. Might as well mention AKA. The word global may be used instead of absolute. I.e., you can hear someone talk about the global max. So if you see that phrase, they're talking about this, right? So global and absolute, they're kind of the same thing. Another thing so that's 1/20. Another thing you might want to know is that there's the idea of using extreme. So an extreme point is the same as a max point or a min point. And the word extrema is just the plural of extreme. So on some of the files you might see them ask you, find the absolute extrema, right? They really just mean find the absolute maximum. Right? Or find the global extreme values. It's the same as absolute maximum. And that's it. That's the idea behind absolute max and min. We're going to talk about how to find these guys, but I just want you to be able to recognize what they are. Pretty much on the graph is the highest point or the lowest point. In general, right? Now we're going to talk about local maxes and minimums. Right? So there are two classes of maximums and minimums. So again, f is a function the f of c is called, right, c is in the domain of f again, a local max if f of c is greater than or equal to f of x. But here's the distinction: for all x near c, right? Not in general, just like the guys that are close, that are in that neighborhood, right, in the vicinity of c, right? Similarly, f of c is local min, or local minimum, if f of c is less than or equal to f of x for all x near c, right? X near c means x is in some open interval near c, open interval center at c. So the idea is, if you're on a number line and c is right here, then you take some small open interval around it. X is any number in that interval, right? Just in that local group. Like you're zooming in and you're just looking locally, not in general, but locally. There are other phrases you might hear this referred to as well. You might see the word relative used instead of local. So they might call it the relative maximum or the relative minimum. It's bad taste, but if they neglect to say which kind of maximum or minimum they're talking about, whether absolute or local, people usually refer to the local for some reason. So it's very common. It's not right, but it's very common. So I think I should tell you guys about it.
Is it because like locally you get more precise information?
Yeah, because you usually care about locally anyway, right? So you usually, you never want to look at everything in general. So usually when someone says, "Oh, find the maximums and minimums," they usually mean find the local ones. Commonly neglecting absolute or local refers to local by default.
If the parameters aren't defined though, how do you know where to say local?
Oh, in general, you look at the whole domain, right? If they don't want you to look at the domain, they'll actually give you an interval, right? But if they don't, you look at biggest possible. But for the local, you actually don't really care, because you're only looking locally anyway. You're never looking at a big gap. So let's do some illustrations for this. So determine the local maximums and minimums here. Okay, let's talk about this one. Local maximums and minimums, where do they occur?
Would the local min be on the right one? Like the one that swoops down below the x-axis?
Here?
Yeah.
Yep, that is called, that's a local min right there. Right? Right, because when you zoom in,
Yeah.
right, that point here is smaller than every other point, right? You don't look in general, you kind of zoom in, right?
Same thing for the next one there, right?
Same thing would be right here, that's also a local min. Right? Same thing right here, this is also a local min.
I thought if there was like a local, it would have to continue on the other side. It couldn't just end.
No, not by our definition. Guys here, these are local maximums. Right? So obviously anything that's at the bottom of a valley is a local min, that the top of the hill is a local max, right? What about this guy?
That doesn't exist.
It doesn't exist, there's no point. So you're kind of always increasing to that point but never getting there, so there's no local max there. This guy cannot be a local max either, because if you open some interval, there are points right beside it that are higher than it. Right? So those are all the local maxes and minimums here. Notice that this guy, you can actually be both a local and absolute. Like this guy here is also an absolute min, right? So he's a local min and an absolute min, right? So not only is he smaller than every guy in his region, but he's pretty much smaller than everyone in general, right? So you can be both.
Is that normally the case for like absolutes? Like they usually are like the local one.
Yeah, well, an absolute is always going to be a local one, but locals aren't always absolutes.
If you were to take your dotted line and start moving it to the right, as soon as it touches that line, would that be your maximum or minimum? Sorry.
Touches what line?
Your dotted line starts moving to the right.
Yeah, my dotted line here represents an asymptote.
As soon as it intersects with your line function,
This one?
yeah,
Yeah, what about it?
wouldn't that be your local min?
No, not necessarily. Local min just means you're the smallest in some region. It's not a matter of who intersects with water, right?
Yeah, but you'd be focusing your region onto that line.
Oh, you mean if for some reason I cut off here, right, with something?
That's your.
Then
that's
yes,
your,
this would be a local min.
Okay.
That pinpoint.
Like if you were to only look.
Yeah, because you'd only zoom in there, it'll be the lowest point.
Yeah. Okay.
So what like when we're looking like locally, like what parameters do we have to do? Like every like what x values or like you know what I mean? Like what I guess
The scale.
No, you're,
Scale.
yeah, well, you're kind of looking for hills and valleys.
Okay.
It's kind of what you're looking for. So you open like this wide, you have two hills, that's obviously too wide. So you start to look for single quantities, single spaces where this happens. Right, so here you'd have local max, right? Also here, also here, also here.
and
Right. You have local mins. One is here, one is there, one is there. Here you have a local max as well. Also, it's an absolute max. Right? This point here is higher than every other point on this graph. Right? This local min here is also an absolute min. Similarly here, this is local, max, local, max, local, max. Here's a local max because he's actually filled in. There's no local max here because he's not filled in. Here's a local min. Here is a local min.
And that's
It's also an absolute min, so it's an absolute min. Here's a local min. Here's a local min. Here's a local min.
on the top one, that's a local min too, right?
What, top one?
Top on the far left. No, up top graph. Top graph.
Up here?
Yep, furthest left.
This, yes, this is also a local one. Here?
You only have an absolute and local max.
Alright, this is just a local max, which is also an absolute max. And there's no local or absolute min. It's always going down. So points like these, some reasons why we care about points like these, I hope would be obvious. So let's say, for example, these functions are representing, your profit that you're tracking, right? You'd want to know where all the hills and valleys are, because it's obvious that things were going well until this point, and then something happened, and I started losing money. You're going to want to know what happened right there, right? Right? You're going to want to go local. You're going to want to know what was happening just before that, where I was making money. Why did I peak here, and why did I start losing money, right? You're going to want to zoom into these things. Usually like a max or a min, there's a lot of information there that you're going to want to find out, right? So these, remember, functions, they aren't just pictures on a board. They're always going to be representing something. So you want to know when something hits a peak or when something dips to a valley. Things like that, there's a lot of important information there. You can talk about the behavior of something just by looking at those guys. So finding maxes and mins are, in general, pretty important stuff. But so far, the only thing that we really know how to find max and min with like calculated precision is like the vertex of a parabola, right? So, the x value has to be minus b over 2a. We want to generalize this idea. How do I find this random function, right? If you gave me the equation of this guy, how would I know where all the maxes and mins happen, right? There's no general vertex formula for a general function, right? So that's where calculus is going to come in. But
Quick question.
yeah.
The local max on this graph?
On this one?
Yeah.
Here?
Yeah, the local max.
Yeah.
Why is that not always the one further over? The dot. Other way.
The local,
Yes. Why is that not also an absolute max?
It is also an absolute. Okay. Right? Because if you look at this, he's larger than everyone else. Yeah.
Okay.
Yep. Yeah. All right. So we have some theorems here that I'll just mention them. You can't go through a calculus class. I've never heard of that theorem, so I'll just mention them. There are things like the extreme value theorem, it's called. In this class, I won't actually prove any theorems or actually to use theorems to prove anything, but you should know some of these general statements. This is the theorem that says if f is continuous on an interval a, b, on a closed interval. So remember, continuous means you can draw it without lifting your pencil off the page. You can also talk about that in terms of limits. But say a function is continuous on a, b, then it will, as in it's guaranteed, to attain both an absolute max and an absolute min on a, b. This is called the extreme value theorem, right? It says that the existence of absolute maxes and mins are guaranteed on any interval where your function is actually continuous, right? So you'll notice that in most of my examples where we couldn't find absolute maxes and min, it's in cases where we had a hole or an asymptote or something messing up, right? So as long as your function is continuous, there will always be a point that's an absolute max and an absolute min, and of course we will want to find it, which I'll talk about later. There's also something called Fermat's theorem.
Last theorem or
No, not the last theorem. Obviously one of the previous ones. Right, so Fermat's last theorem is that one that talks about things that look like Pythagoras' theorem. So not that one, this is a different one. It's talking about maxes and minimums. So it says if f has a local, and this term really gives us a clue for things that we're going to be looking for. If x has a local max or min at c, and the derivative at c exists, then the derivative must be 0. So this is the theorem that says if you have a maximum or a minimum and your derivative exists there, and I also believe f has to be continuous. Right, so as long as you're at a point where you have a max or a min, where you know beforehand there's a max or a min, and you can actually find a derivative, the derivative must be 0. One thing you should note here, note the converse is not true. Converse is a reverse statement, right? So I said, if this happens, then that will happen. It's not always true that if this happens, then that will happen. In fact, in this case, we know it's not true. So an example would be something like y equals x cubed. Right? Now if you look at that function, and what if I ask you y, if that's f of x, and I say, what's f prime of x? Well, that's just 3x squared. Note, if x equals 0, then f prime is 0, but there's no max or min at 0.
Oh, is it because this is the point where it's changing, like going like down?
Right. 0 is here. What?
Is it like that theorem true because it's point when it goes up, it has to have like a rate of change that it can't increase so that it can go back up that way?
Yeah, so this is talking about things that look like hills or valleys. So it's talking about at some point you have to be decreasing and then increasing, you have to pass 0 at some point, right? Or the vice versa. You have to be increasing and decreasing, you have to pass 0 at some point, as long as your derivative exists. There are cases where your derivative won't exist at all, but it's actually a max or a min. So I'll give you another example of that. Also, you can have max or mins where f prime does not even exist. Okay, anyone give me an example?
X equals 2.
Like y equals?
No, f prime exists for 2, right? If f of x equals 2, that's a constant, the derivative is 0 everywhere. So it actually exists.
Would it be like absolute value? Say?
Absolute value. Y equals absolute value of x is one example. We proved earlier that the derivative at 0 does not exist, right? Because the limits didn't match up. If you take the derivative limit from the left, from the right, you get +1. If you take it from the left, you get -1, right? So the derivative at this point doesn't exist, but that's clearly a minimum. Right? So it doesn't. So this theorem doesn't work in the reverse order, right? So if your derivative doesn't exist, or you know the derivative is 0, all bets are kind of off. You kind of have to test some other way. Right, so because of these two examples, we come up with this other idea. So there's another idea here of what we call a critical number. That is a function. C is in the domain f. Then C is called a critical number. If f prime of c equals 0 or f prime of c is undefined. Right? So because of Fermat's theorem, we kind of think that where the derivative hits zero are places we kind of want to look at. Also, because of examples like this, we also know that where the derivative doesn't exist is also places we kind of want to focus on, right? Because things like this can happen, right? So whenever things like that happen, we say that's a critical number. Those are things we have to focus on. And you might hear the phrase critical points as well. And in this case, C, f of C is called a critical point. Right? Obviously, f of C would be called the critical value, right? So there are all these terms that are pretty typical. Okay. So now we know what they are. Let's talk about defining them. So there's something for absolute maximums and minimums. This is called the closed interval method. So it says to find the absolute max or min of f on an interval AB, right? It has to be a closed interval AB, called the closed interval method. One, what you would do is you would find all critical numbers C in AB. And find f of C for each. 2. You evaluate f at the endpoints. Find f of A and f of B. Three, compare the values of parts 1 and 2. The largest value will be the absolute max. The smallest value would be your absolute min. Forgot to mention this earlier. This works when f is continuous. Right, this is called the closed interval method. This is actually a method to find an absolute max or min of a continuous function on a closed interval. We're talking about local max and min. Alright, so this is a method for absolute max and min on a closed interval. Talking about local max and min, there's also a method for that. There are actually a couple methods that are useful. Personally, the first method is the one I'd recommend the most. and use most often. I pretty much never use the second one, but some people like it. It's called the first derivative test. And I've actually kind of described this to you before in that huge table where I was talking about the different functions and how they behave. Right, so this is called the first derivative test. 1. Find out critical values. Two. Usually you want to test the signs in between them, but I'll actually describe what I'd recommend you do. Plot these on a number line and test values in between them. In the first derivative. That's why it's called the first derivative test. We're going to use the first derivative all the way. So you're going to use the first derivative to find the critical numbers, right? Basically, remember this means that your f prime is going to be 0 or your f prime is undefined, right? So you're going to find all numbers for which that is true. You're going to plot them on a number line and you're going to test values in between them, right? 3. And we care about the signs here, not necessarily the values themselves. F prime positive means increasing. F prime negative means decreasing. And we have maximum occurs if at that critical number C, I plug in a value over here, my F prime is actually increasing on this side, right? So I get a positive number when I plug into the derivative, and my F prime is decreasing on that side, which means I have a negative number when I plug into my derivative, right? And at this point, F prime equals 0, or F prime undefined, but of course F itself is continuous. Right? That's how you know you'd have a max, right? If you go from a plus to a negative, you know you hit a max, right? And a min happens very similarly. It means if you're decreasing on this side and you're increasing on that side, right? So on the left, your F prime is negative. On the right, your F prime is positive. And right here, your F prime is 0 or undefined, but F itself is continuous. That point actually gives you a mean. This is called the first derivative test, right? So you're always plugging numbers into the first derivative. Two, there's also something called the second derivative test, but I pretty much never use it, but you can use it if you'd like to. As the name suggests, this uses the second derivative. So in step 1, again, you find all critical numbers. So you find the derivative, set equal to 0 undefined. Just do all that. Then you have to find the second derivative at double prime. Third, if f double prime is negative at C, then this gives you f double prime is positive at C. Right, where C is a critical number. What do you think will happen if double prime is negative at 7? What does second derivative negative mean?
That's where the concavity changes.
No, concavity doesn't change. When it's negative, it has a certain concavity. What is that? Down. You're negative, you're down. So, right? Down like a frown, right? Which means you shape like this, right? So what kind of extrema do you think that points to? That's a maximum. Right? And if the second derivative is positive at a critical number, that would be a minimum. Right? As in a local max and a local minimum. That's called the second derivative test.
Why do you not use that? That seems very straightforward.
Because usually in most contexts where you're doing this, you'd have to kind of go through this first, and then that. So that kind of becomes pointless after a while. Right? Really, where we're going here, we really want to start being able to plot functions and talk about behavior. So even talking about not only maxes and mins will be important, but where it's increasing or decreasing. Right? To figure out where something is increasing or decreasing, you would do this. So if you already went through the trouble to do this, there's no point in doing that. Right? So in most contexts where we're actually going to be using this stuff, we'll have to kind of do this sign chart anyway. So it's not really going to... In practice, I haven't had a reason to use it because I've already gotten my information that I need from the first derivative to determine it. And besides, in general, sometimes, like, even if you don't really need that, remember, sometimes your function is complicated, right? Maybe it's something you have to use quotient rule or some kind of crazy rule. You don't want to take another whole derivative if you already went through a lot of trouble to get one of them already, right? I'd rather just plug in numbers into this function that I already found than have to compute a whole other function just to plug in numbers again. It seems like it's either a lot more work or it won't be necessary. Yeah.
I remember with the position function and summation thing, you said like there's like a third one that give you drag. It's like third. Do anything in this?
No, not for our
Not
purpose.
for like.
It won't be useful to us. In terms of the shape of a graph, the third derivative is not going to do that. It's not something you'd be able to draw by hand. So let's actually do some examples. Let's put this to work. Squared. C equals x cubed. There's also part F, but I'll save that part. That one's a bit more interesting. Okay. So there are some times when we can actually use graphs to talk about these things. And the last one. Right, so y equals x looks like that. Right? And we're not given any restriction of the domain or anything, so what can you tell me about this one?
There's nothing. There's no
There's
absolute,
no extrema. No absolute extrema, no local extrema. Right, you can tell that from the graph very quickly. Okay, that'll just keep going up, that'll just keep going down. What about this one?
So there's only going to be one minimum, that's it.
Right, so we have a local minimum, which is also an absolute minimum, by the way, at what?
0.
At x equals 0. Right? And the local min equals absolute min is equal to f of 0 equals 0. What about this one?
Same as for the first one.
It's a cubic. No local min, no local or absolute min. This one looks like that.
It's the same as B, where there's only one local min at 0, and that's it.
You have a local min, which is, by the way, also equal to the absolute min, which is f of 0 equals 0. This guy.
The global maximum, but there's only one, the minimum and at 0.
Right, there's local min and absolute min is f of 0 equals 0. That's my f of x. Okay. Those are obviously too easy, right? Because they're graphs you know by heart at this point, so you'll be able to, graphs you know by heart, you'll be able to tell a lot of them where things are going on. Let's make things slightly more complicated. Not much more complicated, but slightly more complicated. F. Here's my function. Y equals x to the 4th minus 4x squared. And I'm now going to give you an interval on minus 2 to 3. Find the local and absolute extreme of that function. Do you know how to graph that? You will pretty soon. Well, actually, from pre-calc, you should remember how to graph things like that, actually. Not in as great a detail as we're going to be able to graph things now, but you should be able to sketch that roughly.
Would it look like an M? Or like a W?
It would look like a W, right? So it's probably beneficial for me to just run through a sketch on the level that you would sketch this in pre-calc, right? So how would you sketch this in pre-calc? What are the first things you kind of look for when you want to sketch a graph?
You look for the power of the,
Right, the highest power is a 4, so we know the end behavior, both sides are going to go up because it's positive. All right, what's the next thing you look for?
Minus whatever.
Minus what?
So you also know what the graph of x squared is?
Sure, but how does that help?
That's
So the first thing you kind of want to do is the domain. Obviously the behavior of the function based on the highest power is something that we also look at. But the next thing you're going to want to know about is intercepts. Right? If you're graphing anything, you're going to want to find x and y intercepts. So let's look at the, we're going to do this from the picture, but I'm also going to do it with the calculations, the way using calculations as we found before. So first thing you want to do is find intercepts, right? What's your x-intercept?
0.
You set y equals 0, you solve for x. How do you solve for x?
Factor out the to an x squared.
It's x squared, you get x squared minus 4, so you get
X squared and then 2 parentheses x plus 2 x minus 2.
So you have x equals 0, you have x equals 2, you have x equals minus 2. And notice at your x equals 0, it should behave like a squared function. Now, we also find the y-intercept, which is, we just plug in x equals 0 and solve for y. So that's 0 to the 4th minus 4 times 0 squared. So you just get y equals 0. Okay, no problem. And basically, in pre-calc, that's pretty much all we had to know, right? You go here, you start graphing this guy. You'd write in your intercepts, which are 0, minus 2, and positive 2. Now, in pre-calc, you know it's a graph, it's a 4th power, so you know that the right side has to be going up, and the left side has to be going up. And so you really want to know what's going on in the middle. And so what you would have done when you're in pre-calc is test a point in between here. Like, see, you test a 1. So you take a 1 and you plug into the original function. This will be positive, this will be positive, this will be negative. So then that means your graph is below the x-axis because it gives you a negative value. Then you plug in something like a minus 1. This would be positive, this would be positive, this would be negative. You get a negative again, so you know your graph is down here. So you know you draw your function looking like this. So you're down here because you tested a point it's negative, but you have to come back up to hit this intercept. So you're going to turn around, and you're going to come up, hit this intercept. But then you know you have to be negative again because you tested that point, so you're going to turn around and come back down. But then you have to go back up to hit this point, so you go back up again. And you connect there. So it's going to be a double. Now we don't care about everything, we only care about from minus 2 to 3. So minus 2 is actually here. My 3 is going to be somewhere out here. So beyond this, I don't care, so I forget about that. And beyond that, I don't care, so I forget about that. So that's my picture. Right?
W check.
So it's, yeah, it's a W check, I guess. So clearly now we can sort of see where the guys are. We have local minimums here. We have a local maximum here. We have a local maximum here. We have a local and an absolute maximum here. Now the question is, what are actually these points? It's clear that the endpoints are fine. This 0 is fine. But what is actually the x values that will give me this dip, right? Is it actually symmetric? Is it going to be halfway between it, minus 1 and 1? How do we actually figure that out? Now we go to those methods that I told you about earlier.
Hey, don't you just set the derivative of find the derivative of this thing and just set it to 0?
Let's do the absolutes for absolute extrema. We're going to do the closed interval method. So remember the first thing was to find your derivatives, right? So if your y is equal to x to the 4th, your y prime would be equal to
4x cubed minus 8x.
right? Now remember, for critical points, y prime equals 0 or undefined. Now your y prime is a polynomial, so it's never undefined, so we only care about where it's 0 is, right? This is not going to happen because it's a polynomial, right? It could happen in general, though. It doesn't happen here. So what I'm going to do now is set this guy equal to 0 and see if I can find solutions. How do I solve that?
Take out that.
Take out the x.
I can factor out a 4x, right? And then I would get what? X squared minus 2 equals 0. Which means x equals 0 is a critical point. Also x equals plus or minus radical 2. So it turns out we didn't have symmetry. It's not halfway between these, right? That point actually occurs at, we know what the graph looks like, so I can actually start filling it in now. It's a minus radical 2 that hits the lowest point. And it's a positive radical 2 that hits the lowest point here. But we could know that before even looking at the graph, right? I just drew this graph for your edification. Let's actually keep moving. Let's see if we can identify what we know as the absolute max and mins on minus 2 comma 3, right? But this is the first, now note x equals 0 plus radical 2 and minus radical 2 are all in right? You want to be in the interval of consideration, right? If I had one of these numbers that's outside this interval, I wouldn't care. I just ignore it, right? I only care about what's in between these, right? So now keep going. So I know that they're all in there. So what I'm going to do is I'm going to evaluate f at all those points
In the original function.
in the original function, right? Remember, it's the y value that we're after, right? So f of 0 in my original function is just 0. F of radical 2, plug into the original function, I get radical 2 to the 4th minus 4 times radical 2 squared. Radical 2 squared is 2, square that again, so this would give me 4. Radical 2 squared is 2, so what is that? 4 minus
8.
2 squared.
No, you
It's,
get radical 2 squared.
Yeah, it's radical 2. It's just 2, so that's 4 minus 8, which gives me
So negative 4.
minus 4 is going to be the lowest value.
And this is basically the same.
It's going to be the same because I have even power, so whether I plug in a negative or a positive, it gives me minus 4. Okay, so far so good. So the next step is to evaluate f at the endpoints. So I want to know, I'm saying y equals f of x, of course. So I'm going to do now is say f at the endpoint, the far left endpoint was a minus 2. So that's going to be minus 2 to the 4th minus 4 times minus 2 squared. So that's going to be what? 16 minus 16, 0. And I evaluate f at 3. Right? So here what I just did was I test the critical points. And now here I'm testing the endpoints. This is the closed interval method. So f of 3, I'm going to have 3 to the 4th minus 4 times 3 squared. 3 to the 4th is what, 81?
81, and then 9 times square is 36. Will be, that's like 40, whatever. I think it's 45.
What? Is it 45? Yeah, that's 70, and then this is 11. Yeah, so that's 45, right? So now in the third step, so in the first step of the closed interval method, the biggest step, you find all the critical numbers and you evaluate the function at these critical numbers. Then you just evaluate the function at the endpoints. In the third case, you just compare all of them. So of all these numbers that you found, you're going to look for the biggest one. What's the biggest one? 45. So here you're going to say f of 3 equals 45 is your absolute max. That's the biggest guy around, right? Then you're going to go again and you're going to look for the smallest ones. Minus 4 is the smallest ones. And also, f of radical 2, which is the same as f of minus radical 2, equals minus 4, is the absolute min. Right? Which, remember, we had our graph. We kind of knew this already from the picture, right? That's what we look at. Clearly, this is your absolute max. That occurs at 3, right? I didn't have to know what the graph looks like to actually know that. And I know that these 2 points here, that was at minus radical 2, and that is at positive radical 2. Those were actually the lowest points on the graph. Right? And the closed interval method allowed me to identify them just from the calculations. This is going to be a lot of overlap here, but I just want to start from afresh so you can see the difference. When you're looking for an absolute max versus a local max or a min, how things would go. Local, extreme. Right, so step 1 was to find the derivative. First cube minus x. And then you find the critical points. So you know f prime must be 0 or undefined. this does not occur, but we know that if y prime equals 0 implies that, you actually did this already, x would be 0 or plus or minus radical 2. So now here's how we would test it locally. You actually draw a number line, right? If you care about local and not absolute, you wouldn't do this method here. You'd actually do a number line and test it. So you draw a number line, and I always just write here like the first derivative, so I can remind myself that I'm always plugging into the first derivative. In the future, I'll be plugging into other derivatives, so you want to know that. So 0, minus radical 2, positive radical 2. Right? And what you do is you test numbers in between them. Right? So I test the number over here, like a minus 2. Well, it's in between. It has to be in between. Remember, we're not doing everything. We're only from minus 2 up to 3. So a number that's between here and here, which would be what?
Minus 1.
Yeah, minus 1.5 or something like that, right? You'll test it in this guy, you'll realize that you'll get a negative number, right? Put a number in between here, like a 1, you realize you get a positive number, right? So this means your function is decreasing here, it's increasing there, right? Plug in a number here like a 1, this should be a minus 1. Plug in a number here like a 1,
That should
this would actually give you a negative number if you actually plug into this function, right? Which I always recommend plug into the derivative function, which I'd always recommend to factor it. It's easier to plug in the factors and say, oh, it's a negative times a positive, right? If you plug a number over here, like a 2, into this function, you get a positive. So now you're doing this. So I test a minus 1.5, gives me that. If I test a minus 1, gives me a positive. If I test a 1, gives me a negative. If I test a 2, gives me that. And so what I can say from this guy is that this guy is a minimum, right? Because I'm decreasing here, increasing there. 0 is another critical point. That guy is going to end up being a maximum, a local maximum, right? Because I'm increasing, then decreasing. Look at this guy here, that guy's a minimum. Because I'm decreasing, then I'm increasing. And it's a polynomial, I'm always continuous, right? And this kind of tells us what's actually going on in the picture. It says when I'm at minus radical 2, I'm a local minimum. If I'm at 0, I'm a local maximum. If I'm at positive radical 2, I'm a local minimum, right? And you can do all this by plugging into the first derivative and checking the signs in between the critical numbers. For now, we'll stop there. That actually completes the section. So you can do 4.1 and 4.2 for homework tomorrow, and I'll have the test for you ready by then.
When's on 3.6?
Tomorrow. Yeah, 3.6, 4.1, 4.2.